Hey, the Sioux Falls physics teachers are with you here. Thanks for joining us. We are going to be looking at an impulse and momentum problem here. So we got Gary the golfer. He's going to hit a .05 kilogram golf ball with a force of 130 newtons. And the contact period between the club and the ball is just a fraction of a second, .025. All right. Question is, what is the impulse that is exerted on the golf ball? And what is the resulting velocity of the golf ball after this happens? Okay, let's start with the impulse, okay? That's our first key here. We know that the impulse is a change, okay, in momentum, all right? And one of the ways that we can find the impulse is to take the force that is exerted on an object multiplied by the time that that force is exerted. Okay, and that's what we'll use here because we know that a force of 130 newtons was applied for .025 seconds, and so that can give me my change in momentum or my impulse. So 130 newtons multiplied by my .025 seconds, okay? And when I do that, I get an impulse of 3.25. Now, what are my units on an impulse? Well, it's a change in momentum, so momentum is measured in, again, kilogram meters per second. All right, so that would be my measurement for my impulse. Now, what about the resulting velocity of the golf ball? Okay, well, now that I know how much the momentum changed, I can figure out how much the velocity changed. Remember, we're going to assume the golf ball started at rest, so it had zero velocity, had zero momentum at the beginning. We know it's going to end with the momentum that we just calculated then, the 3.25. All right, so momentum, again, is equal to mass times velocity. That's one of the ways we can calculate the momentum of an object. And I do know the mass of my golf ball, right? It was given to me at .050 kilograms. All right. And I don't know the velocity, but I do know, again, the momentum, or the impulse value, okay? And so what I'm going to end up doing is setting 3.25 equal to .050 times velocity. And now I can solve for velocity by doing a little simple division there, and I get a velocity of 65 meters per second. Hey, welcome back. Here we've got another impulse and momentum problem for you. This time Rhonda, who has a mass of 60 kilograms, is riding at 25 meters per second in her very fast sports car. She suddenly has to slam on the brakes, though, to avoid hitting the innocent dog crossing the road. But fortunately, she is wearing her seatbelt, and that slows her body down to a velocity of 5 meters per second, and the time there is .400 seconds to do that. We want to figure out, though, what's the force on her body by the seatbelt to slow her down, all right? Okay, so first thing we're going to have to look at here is we clearly have a situation where Rhonda's velocity is changing. So anytime we see that change in velocity, that should be an indication to us, yes, we are going to be thinking about a change in momentum or an impulse. So before we can even get into figuring out the force that's exerted on her, we need to figure out, okay, what is going to be the impulse exerted on her as she changes velocity? Okay, so the impulse, which is represented by J, is going to be equal to the mass of the object times the change in velocity. So in this situation, our impulse is equal to her mass, which is 60 kilograms, times her change in velocity, okay? Well, she has a final velocity of 5 meters per second, and she started with a velocity of 25 meters per second. So I'm going to take 5 minus 25. She's slowing down, so we would kind of expect to see a negative impulse here. And in this situation, we would get negative 1,200. All right, and again, the units on this are kilograms meters per second. Okay, so that shows the impulse that is acting on her body. Now that we have the impulse, then we can start moving on now to the force that is exerted on Rhonda. Okay? Remember that the impulse, all right, J, is also equal to a force that is applied over a period of time. Okay? So now that I know that the impulse is negative 1,200, I can find the force because I also know that the time that this braking or this stopping occurred was 0.400 seconds. Okay? So doing a little division there, I get a force applied to her of negative 3,000 newtons. Okay? Now, a negative force indicating that that force is being used to slow her down or de-accelerate her as the car slows down itself. All right, so that's a good example there of, first of all, finding the impulse of an object and then using that impulse to figure out the force that is exerted on the object as a result of that.
Well, hello everyone. Welcome back to the Sioux Falls Physics Teachers, looking today at impulse or change in momentum from a graph. And again, this is one of the more important applications of impulse. It says the graph below shows net force versus time for a 1 kilogram object. Determine the velocity of the object at a time of 10 seconds if we have initial velocity of 0 or if we have an initial velocity of 4 meters per second. Well, the first thing we need to do is deal with our graph. And notice over here that we start at the origin, 0 seconds and 0 net force. It moves at 2 seconds up to a net force of 6 newtons. Okay, and then in the next 2 seconds, okay, so over here at 4, it continues that steady amount. And then at 4 seconds, it begins to decrease all the way down to the total, which is 10 seconds. And at that point, we're back to a net force of 0. Well, the first thing to remember, and this is again kind of just a graph reading skill, is that the change in momentum or impulse can be found by multiplying net force times time. On a graph, if we have net force on one axis and time on the other, that means that we will find that from our graph using the area. So the first thing we want to do is split this up into 2 different segments. We have the 2 triangles, one at the beginning and one at the end, and then we have a rectangle in between. So for our first triangle here, again, triangle is 1/2 times base times height. The base of that triangle is a time of 2 seconds. The height of that triangle is 6 newtons. The next segment that we want to use is the rectangle. And again, hopefully this whole area thing at this point will be pretty familiar to you. For the rectangle, it would just be base times height, which would be 2 seconds and a height of 6 newtons. And then finally, we have the larger triangle over here at the end. And again, it would be found with 1/2 base times height. The base is a time of 6 seconds. The height, again, is 6 newtons. And now we can go ahead and total these all up. For our top triangle, we get a difference then of 6. And again, our label would be Newton seconds. For the bottom triangle, or for the rectangle in the middle rather, we get 12 Newton seconds. And for the bottom triangle, we get an impulse of 18 Newton seconds. Totaling those all up then, we have 6, 12, and 18. And we now get a total change in momentum of 36 Newton seconds as the impulse from the entire 10-second graph. Now that we have the impulse, the question really asks, what is the velocity of the object after 10 seconds? So again, this is kind of worth writing out a little bit of an extra equation. We can say that the final momentum of an object would be equal to its initial momentum plus the change. So in the situation of situation A, it begins with initial velocity of 0. Okay, so it has 0 momentum to begin with. We have just determined that there's a total of 36 Newton seconds is the change over the graph. And then that can be set equal to the final momentum. Well, momentum is mass times velocity, so that could be written as mass times the final velocity. Now, the nice part about this problem, the mass has been given as 1 kilogram. So we would simply be solving this equation. 1 kilogram times the final velocity is equal to 36 Newton seconds of momentum. That leaves us with a final velocity then of 36 meters per second for part A of the problem. Now the second half of this asks what happens if we have an initial velocity of 4 meters per second. The nice part about doing this problem with momentum is that it is very easy to account for the fact that it's already moving. We're going to use this exact same equation here. We will then again have mass times final velocity, only this time we do have an initial velocity, so we do have an initial momentum. So we simply take mass times its initial velocity to get its beginning momentum, and then we would add on again the change. Okay, we have 1 kilogram as our mass. Final velocity is our unknown. Here we have 1 kilogram. Our initial velocity is 4 meters per second, and then we could add on that change that we calculated from the graph of 36 Newton seconds. Solving that out for final velocity, we get a final velocity of 40 meters per second in this situation.
Hey, we're going to do a little amusement park fun here with you guys, a little conservation of momentum. This is the Sioux Falls physics teachers, and we have a situation that we've all experienced at the amusement park when you're in those fun bumper cars, right? We have Ted, who has a mass of 300 kilograms. That's his mass of him and the car, but Ted's probably a pretty big eater too. He's going at 10 meters per second. He's going to bump into poor Melinda, who's just sitting there innocently, not moving at all. Melinda only has a mass of 125 kilograms. And after the collision, we know that Ted continues moving on with a velocity or speed of 4.12 meters per second. We are going to try to figure out what happens to little old Melinda here after this collision. So, key thing here, as the title says, is this is a conservation of momentum. Remember, for any collision we have, momentum must be conserved. We cannot lose, we cannot gain momentum as a result of a collision. So, one of the ways to think about this would be the following, all right? The momentum that Ted has before, so I'll say TB, plus the momentum that Melinda has before, has to equal the momentum that Ted has after plus the momentum that Melinda has after the collision. Okay? So, we're going to simply use mass times velocity as our calculation for momentum. So the momentum that Ted has before this collision is simply his mass, 300 kilograms, and it's the mass of him and his car, times his velocity of 10 meters per second. Melinda, on the other hand, before the collision, has a momentum of 0. And that is simply a result of the fact that she is initially sitting at rest, so she has no velocity, so no momentum. Now, after the collision, Ted, who still has that mass of 300, is moving at a velocity of 4.12 meters per second. All right, that's his velocity. Melinda, who has a mass of 125, is going to be moving at some unknown velocity, and that is what we're trying to solve for in our equation here. All right, so doing a little calculating here. All right, we're going to have 3,000 on the left side is going to be set equal to 300 times 4.12 gives us 1236 plus 125 kilograms times that velocity. All right, and then we're going to just do a little algebra here. Subtract the 1236, you get 1764 equals 125 times that velocity, and divide both sides by 125. You get a velocity for Melinda of 14.1 meters per second. All right. So both of these cars are going to continue moving on. It's just that Melinda is going to go shooting off there with a pretty high velocity compared to what Ted has. And if you think about the difference in their masses being as significant as they are, it makes sense that Melinda would have a very large velocity compared to Ted's once this collision is over. The name is Bond, James Bond here. We're going to be doing a conservation of momentum problem again, this time involving a situation that occurred in a recent film. 51 kilogram Jinx stands at rest on the edge of an offshore oil rig. As she fires a gun, she's driven backward over the edge and into the sea. All right? We're going to suppose that the mass of the bullet that she fired was 10 grams and its velocity was 720 meters per second. What is that recoil velocity that she experienced as a result of the gun being fired? All right, so we're right back again with a conservation of momentum here. Situation, though, at this point is this. All right, if we think of the mass of Jinx, so I'll just say m sub j, times her initial velocity, all right, plus the mass of the bullet plus its, or multiplied by its initial velocity, all right, we know that that will give me the momentum before for both situations, for both Jinx and the bullet, that is going to have to equal, all right, the mass of Jinx afterwards, multiplied by her velocity, plus the mass of the bullet afterwards times its velocity. Okay? All right? So again, what we're setting up here is a situation where we look at before the gun was fired being the left side of my equation, after the gun was fired being the right side of my equation. And again, momentum must be conserved here. We know that the momentum of both of these objects is 0 before the gun is fired. How do we know that? Well, the velocity of Jinx and the velocity of the bullet are both zeros. Okay, so this is a value of 0, this is a value of 0. So my total momentum before the gun is fired has to be 0. All right? After the gun is fired, we definitely have some movement. Okay, we know that Jinx has a mass of 51 kilograms. We do not know her velocity as she goes flying off the oil rig. That is what we're trying to find. So I'll just say velocity of our character Jinx. plus now the mass of the bullet. Now we have to be careful here. The mass of the bullet was given to us as a unit of grams, so 10 grams. So we need to convert that to kilograms. That's going to be 0.01 kilograms. That's very important. We've got to make sure we're staying in our standard SI units. And the velocity that that gun was fired at, the bullet was fired at, was 720 meters per second. Okay? So now we have a simple problem here that we can solve for the velocity that Jinx will have. Now, one thing that we should note here is we should expect to see a negative velocity. And the reason for that is, remember that this whole left side or right side of my equation here has to end up equaling 0. Okay? So they have to cancel each other out, and that's exactly what will happen here. We'll end up getting a value for Jinx for her velocity of negative 0.141 meters per second. Now, what is the negative indicating? Simply indicating that Jinx is moving in the opposite direction that the bullet is. All right, the bullet, let's say, is moving to the right. That means Jinx would be recoiling her velocity to the left. All right. Hey, we got a little train safety here for you. Remember, always look both ways before you're crossing those railroad tracks, but this will convince you why that's important here. We're going to look at conservation of momentum involving a little train action here. So we have a train with a huge mass, and it is about to hit an automobile that's at rest on the tracks. Uh-oh. The train cannot come to a stop. It's still going to be moving at a velocity of 1.4 meters per second, which is really not that fast, but because of the mass of that train, it's going to have a lot of momentum still. The key thing here is we're going to have a situation where the two vehicles stick together. Okay, so that tells us that we have an inelastic collision here. All right. The wreckage is going to continue down the tracks. We want to calculate what the velocity of that wreckage is going to be. Now, remember, it's inelastic, so we got both vehicles sticking together. They're going to be moving at that same speed as they go down the track. All right, so this is still a conservation of momentum problem. So what we're going to look at again is we're going to look at the mass of the train times the velocity of the train plus the mass of the car times the velocity of the car is going to equal, now remember this is an inelastic collision, so they're going to stick together at the end. So we're going to have really mass of the train plus mass of the car multiplied by some new velocity. I might call it like v prime here, okay, at the end. All right, so again, the left side of my equation is before the collision happens, right? The right side of the equation is after the collision happens, and again, momentum must be conserved. All right, so let's start plugging in some info here. Mass of the train, that's 4.5 times 10 to the 5th kilograms. Big train. Only moving, though, at 1.4 meters per second. Okay? Momentum of the car is going to be 0 because it has 0 velocity. It's just sitting still there. Afterwards, again, I've got those two masses that I need to plug in here. So I've got my 4.5 times 10 to the 5th plus mass of the car, which is 1,800 kilograms, multiplied by that v prime. And it's the v prime that we are looking to solve here. All right, so let's do a little calculator work here, get some numbers for you. Multiplying these two numbers together, I get 630,000 when I take 4.5 times 10 to the 5th, multiplying it by 1.4. And over here on the right side of my equation, I'm going to add those two masses together. I get 451,800 kilograms and multiplying that by v prime. So just a little division problem here to finish this out. V prime ends up equaling 1.394 meters per second. Now what you notice here is this. Remember, the train was moving at 1.4 meters per second to start out with. Even after this collision, the train barely slows down at all. So hopefully this is enough to convince you you do not want to be in a car when the train is coming.
Bye.